AP Chemistry, we're beginning a new unit. This is on acids and bases. It's an important topic on the AP exam, and we'll be spending the next 3 weeks on this unit. So acids and bases are important because they appear in many places in nature and in many everyday applications. For acids, these include foods such as fruits, which contains citric acid, milk contains lactic acid, vitamin C, ascorbic acid, and many others. Industrial products such as batteries, which contain sulfuric acid. Biological processes such as hydrochloric acid in the stomach to assist in the breakdown of food. Acids have a sour taste, and so if you think of lemons, that's basically the characteristics of acids. Bases include cleaning solutions, including ammonia or sodium hydroxide. Those are both bases. Antacids to neutralize stomach acid. Biological purpose, such as plant fertilizers. Bases are usually slippery and have a bitter taste, so just think of a bar of soap. Now this slide is really central. It's to the entire subject, and it's one you need to really memorize by the end of this lesson. Acids produce hydronium ions. Those can either be represented as H plus or H3O plus in aqueous and water solution. Bases produce hydroxide ions, that's OH minus, in aqueous solution, and bases are often referred to as alkaline. Now looking at the H plus and the H3O plus, they seem like they're different. We'll talk about why those can both be used interchangeably when discussing acids. So there are three definitions of acids and bases. The Arrhenius definition was the first one to appear, and the Arrhenius definition defines an acid as a proton, that's hydronium ion donor, and a base as a substance that contains and releases hydroxide ions, OH minus ions. The Bronsted-Lowry definition also defines an acid as a proton hydronium ion donor. It defines a base as a proton acceptor. The Lewis definition. In the Lewis definition, an acid is an electron pair donor and a base is an electron pair acceptor. Bronsted-Lowry is the primary definition used on the AP exam and in introductory college chemistry courses. The Arrhenius definition of bases applies to strong bases, and we probably won't talk about the Lewis definition very much, if at all, for the rest of this unit. So acids are substances that produce hydrogen ions called hydronium ions, H3O+, and that's in aqueous solution. Everything we talk about is in the solution of water as the solvent. So hydrogen atoms consist of one proton and one electron and are electrically neutral. So we learned that back very early on in the course. Often in natural chemical reactions, the proton is ripped away from a compound and leaves its electron behind. So as you see right there, they become separated. At this point, the proton becomes a hydronium ion. An Arrhenius acid and a Bronsted-Lowry acid are both defined as proton donors. So here's a typical acid reaction, and you'll come to learn that pretty much all acid reactions look like this. On the reactant side, you have HCl, that's hydrochloric acid, that's a strong acid. You're adding that to water, that's the H2O, and what will be produced is the hydronium ion, H3O+, and the chloride ion, Cl-. So what's happened here is the proton from the hydrogen in the hydrochloric acid has been passed over to the water molecule H2O, and that forms an H3O. Remember that an element is defined by its protons. So if only the proton of the hydrogen atom gets passed over to the water, it's considered to be a hydrogen atom. It's a hydrogen atom without its electron, but it is a hydrogen atom. And so the hydrogen proton from the hydrogen atom got passed to the water molecule to create H3O+, the extra hydrogen, but it left its electron behind attached to the chlorine. And that's why the chloride on the right side, on the product side, has a negative sign. It has that extra electron. So what really an acid reaction is breaking a hydrogen atom in two. It's ripping away the proton from the acid and having it attached to water or to a base, but that hydrogen atom leaves its electron behind. Only the proton moves over to the water. The electron stays behind, and that's why in this case Cl- has a negative sign. This reaction can be written using the H+ notation for a hydronium ion. And so there it is. It's HCl in the products, in the reactant side. Now there's no water listed there. That's because the HCl is listed as aqueous. In other words, instead of writing H2O, you simply write HCl in aqueous solution, in water solution. On the right side, you kind of factor out the H2O from the H3O+. So instead of having H3O+, you just have H+. And then you still have the Cl-, the chloride ion there. So these both represent the same reaction. One is just, we'll call it the expanded or long form, and the one below we'll call the condensed or shortened form. The HCl donates an H+, a hydronium ion, to a water molecule. Note that a strong acid such as HCl reaction is a one-way irreversible reaction. So the arrow is pointing in one direction. So what that hydronium is, that H+, it's really just a proton. It's the ion of a hydrogen atom that's lost its electron, so it's really just a proton, the one proton that's in the nucleus of a hydrogen atom. Once a proton dissociates from a strong acid, dissociate means to break away from, it never reverses and rejoins the conjugate base. Cl- is the conjugate base of HCl. We'll discuss this concept later on in this lesson. But if it's a strong acid, once that H+, that proton breaks away, it will never go back to its acid to reform. That's why it's a one-way reaction. And this is why the arrow points from left to right only. So H+ and H3O+ mean exactly the same thing. So there you have the two representations there. So H+ and H3O+ are both called hydronium ion. This seems tricky at first because H+ is just a proton, while H3O+ is a proton attached to a water molecule. This is because the H+ does not simply float in water solution. It doesn't just jump off from the acid and decide to go out for a swim. In the absence of a stronger base, the H+ ion immediately attaches to the water molecule. That's why the H+ broke away from the acid, because a water molecule pulled it away. So it's not going to be out in solution by itself. And that's why we can treat H+ and H3O+ as being the same thing. It really immediately, just instantaneously transfers from the acid to the water molecule. A generic way to write this or any other acid reaction is HA plus H2O produces H3O plus A-. So the HA is just the generic form of any acid, where H is the proton that's going to dissociate, break away, and A is the rest of the acid molecule. So we'll see some examples here. The other way you can write this is in the abbreviated condensed form is HA produces H+ and A-. H+ represents the dissociated proton, and A- represents the rest of the molecule. You will use a generic equation if you are not familiar with the acid name. I'll show you an example here in just a moment. All acid reactions behave the same, so you can use this generic notation up above for any acid reaction. Example, write the reaction for the dissociation of benzoic acid. So your first thought is, well, I don't know the the chemical formula for benzoic acid? And the answer is it doesn't matter, because all acid reactions can use the generic form. So if you don't know the formula for benzoic acid, you can write the reaction in generic form. HA will produce H plus aqueous and A minus aqueous. Or the expanded form, the extended form, HA plus H2O produces H3O plus A minus. Again, those two reactions are exactly the same. They mean exactly the same thing. They're just different ways that they're written in acid-base chemistry. As long as you have the necessary values for concentration and Ka, that's called the acid dissociation constant. It's the equilibrium constant for a weak acid. We'll talk about that coming up. You can analyze the reaction for benzoic acid. So as long as you have the appropriate numbers, in other words, you can still analyze this reaction without knowing the formula for benzoic acid. Here are a few more examples of Arrhenius and Bronsted-Lowry acids. So this is perchloric acid, and that's the abbreviated form for it. So you can write that in generic form like this. So the H represents the proton, and the A minus represents everything else in that acid, the ClO4, and with the electron left behind from the proton dissociating, it becomes ClO4 minus. Okay, so here's the expanded version of that same thing. And so you can write that as HA plus H2O gives you H3O plus and A minus. So again, the H is simply the proton in that acid, and the ClO4 minus is everything else. Here's nitric acid. This is a strong acid, as was perchloric acid up above. And so that can break apart into H plus and NO3 minus. So in the generic form, it's HA, and the H plus is the proton, and the NO3 minus is the rest of that acid molecule with the electron left behind. So an Arrhenius base is defined as a hydroxide OH minus producer. So NaOH produces Na plus, that's the sodium cation, and OH minus, that's the hydroxide anion. According to the Arrhenius definition of a base, a compound must contain an OH that can be dissociated in water. So we know that sodium, if you remember your solubility rules or go back and check them, sodium dissociates, dissolves, or breaks apart from anything. Hydroxide generally doesn't break apart. Again, looking at those same solubility rules, hydroxide generally doesn't break apart, but in this case, in the case of sodium, it does, because sodium breaks apart with anything. So you have Na plus and OH minus. A Bronsted-Lowry base is defined as a proton acceptor. So here's an example. NH3 plus H2O produces NH4 plus NOH minus. So if you look at the Arrhenius came along with his definition of a base, and he said, well, it's producing hydroxide ions, OH minus, in solution, so it must be something that contains an OH. And if you look at that NaOH up above, that contains an OH, so you know that that's going to be an Arrhenius base. But what was noticed later on, and that Arrhenius couldn't explain, is that OH minuses were being produced by substances that did not contain an OH. So NH3, which is ammonia, just like the kind that you have in your house as a cleaning solution, it produces OH in solution, and yet it doesn't contain any OH. So this was a mystery. They didn't understand how it could do that. Well, the way it does that, very simply, is it acts as a proton acceptor from the water molecule. So that water molecule, which is H2O, will send a proton from one of the hydrogens over to the NH3. But that hydrogen will leave its electron behind. So what the NH3 then becomes is NH4, because it just added that proton, that hydrogen proton. Remember, just a proton alone is enough to define a hydrogen. So it goes from NH3 to NH4, but since it's only a proton, a positive charge, it becomes positively charged, so it's NH4 plus. Now what happened to the water molecule? It lost that proton. So instead of being H2O, it's just HO. But usually we write it as OH. And since that proton, when it jumped over to the ammonia, left its electron behind, that's always what happens in acid reactions, then the OH becomes negatively charged. It's a negatively charged anion. So according to the Bronsted-Lowry definition of a base, the compound does not need to contain an OH-. However, an OH- must be produced, but how? So in this example, the ammonia, NH3, accepts an H+, that's a proton, from the water molecule. This produces an OH- in solution, even though the base, NH3, did not contain an OH-. So basically, a Bronsted-Lowry base creates OH- not by the base carrying it into the solution itself, but by breaking a water molecule and stripping away the proton from a water molecule and leaving the water molecule as OH- as a hydroxide ion. How a Bronsted-Lowry base reaction works. So just here's a illustration. So you have reactants NH3 plus H2O. So there they are. There's NH3, there's H2O. NH3 does not contain an OH-, hydroxide ion, but one is created when H2O donates a proton, so water acts as an acid in this case, to the base NH3. So what you see here, that proton moves over like that, and that produces on the product side of your reaction NH4 plus. You have 4 hydrogens, 1 nitrogen, and since it was just the proton that jumped onto the ammonia, it now takes on a positive charge. And over on the water side, the water molecule is no longer a water molecule. It's now an OH, 1 oxygen, 1 hydrogen. And since that hydrogen left its proton, it left its electron behind, it is now OH-. NH3 accepts a proton and becomes an ammonium ion. NH4 plus is called ammonium. So summary. In both the Arrhenius and Bronsted-Lowry definitions, an acid is a proton donor. It gives away a proton. It breaks a hydrogen atom in two. It hangs on to the electron, but the proton then goes away to either a water molecule or a base. This means it gives a proton away to water or another compound in solution. So that's for both Arrhenius and Bronsted-Lowry. They both have the same definition of an acid. In the Arrhenius definition of a base, the base must be a compound that contains the OH- and that releases the OH-, the hydroxide ion, into aqueous solution. So this definition covers strong bases. In other words, when you look at an Arrhenius base, you see OH in the chemical formula. In the Bronsted-Lowry definition of a base, the base must accept a proton from water or another compound to create an OH hydroxide ion in the solution. Let's look at how a strong acid HCl is created. So all acids are made from nonmetals. This goes back to the foundations unit when we talked about covalent bonds. All acids are made of nonmetals. For this reason, they are bonded by covalent bonds. That is, they share electrons to fulfill the octet rule. Fluorine with 7 valence electrons is joined by hydrogen with 1 valence electron, like that. Both atoms fulfill the octet rule to create a covalent bond. So acids are made up of nonmetals. We now have a strong acid that will react with water. Acids are divided into strong acids and weak acids. A strong acid is one in which all of the H+ protons break away from every acid molecule. 100% of them will break apart in water. A weak acid is one in which only some, not all, of the H+ protons break away from every acid molecule. When a proton H+ breaks away from its acid, it is said to dissociate. So get used to hearing that word dissociate. It means break apart. Dissociation occurs because the hydronium H+ proton is more attracted to one of the lone pairs of electrons on the water molecule than to a chlorine atom, in this case a chlorine atom. Hydrochloric acid, HCl, is a strong acid. All HCl molecules in an aqueous water solution will donate their H+ protons to the water molecule. So that proton goes across and jumps onto the water, onto the lone pair, one of the lone pairs of a water molecule. So this is a hydronium ion. It can be written as either H+ or H3O+. Again, the reason for that is that proton does not just simply jump away from the chlorine for no reason. It's pulled away by the water molecule. Therefore, the moment it leaves the chlorine, it's immediately attached to the water molecule. And therefore, we treat H+, the proton, and H3O+, that entire compound there, as being the same thing. You can write, they both, H+ and H3O+, both represent the same thing. And that's a hydronium ion. Now, the dissociated hydrogen leaves its electron behind. So that gives that chlorine a negative charge, and so it's now called a chloride ion. That's a Cl1-, and you know from learning about ionic compounds that chloride forms a 1- charge, and it has a full octet. So an acid produces a broken hydrogen atom. That's just a simple metaphor to think about it. The hydrogen, which is one proton and one electron, is broken in two. The proton jumps over to the base or to the water molecule, and the electron stays behind with the original acid. A Bronsted-Lowry base accepts the H+ hydronium ion released by the acid. In this example, water acts as a base. Water is both the most common acid in nature and it's the most common base in nature. So you're going to see it behaving as both an acid and a base throughout this unit. It's going to both be giving away that proton and it's going to be taking in that proton. Just depends on what it's reacting with. So in this example, water acts as a base by accepting the H+ ion donated by the HCl. The attached to the water produces a positively charged H3O+ ion. An H+ ion is the same as an H3O+ ion. Both are called hydronium ions because the proton immediately attaches to the water molecule. It doesn't just swim around in the solution by itself. So there it is. That's the hydronium, the H+. So when the H+ proton is pulled away from the chloride, it immediately attaches to H2O. So H+ and H3O+ are both referred to as a hydronium ion. And there you see that. Okay, so there's a lot of repetition in this lesson because you really need to get this concept down clearly before we move on. So the AP standards prefer this symbol for hydronium. So do I in class, for the simple reason that that's actually what it is. It's an H3O. It's got an oxygen and 3 hydrogens and a positive charge. So it's a more accurate description. The formula shows the water molecule as well as the hydronium like this. So this is the preferred way to write it. A strong acid is one in which all of the H+ protons dissociate from the acid. There are 7 strong acids. You should memorize these. The reason is very simple. There are tens and tens and tens of thousands of acids. Only 7 are strong. So if you know the 7 strong acids, that anytime you're presented with an acid and it's not one of the 7 strong acids, then you automatically know it's a weak acid and it will behave as a weak acid behaves. So there are 7 strong acids: HCl, hydrochloric acid; HBr, hydrobromic acid; HI, hydroiodic acid; HNO3, nitric acid; H2SO4, sulfuric acid; HClO4, perchloric acid; and HClO3, chloric acid. Some references don't list chloric acid as a strong acid. Your textbook, Brown, LeMay, Burston, the gray book that you have for this class, lists chloric acid as a strong acid. Another college textbook that I use for reference does not. So why they could not decide, I don't know. But we're going to list it just for the sake of completeness. So we will list chloric acid as a strong acid. So all strong acids completely dissociate in water. All other acids are weak acids and do not completely dissociate in water. There are several other ways acids are classified. So these are the 7 strong acids again: hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, perchloric, and chloric. The first 3 are called binary acids. Acids with a hydrogen attached to a single element. In all 3 cases, it's a halogen from the second to last column on the periodic table right next to the noble gases. Those are called binary acids because they contain 2 elements, a hydrogen and one other element. The 4 down below, those acids with the hydrogen attached to an oxygen compound, are called oxyacids. Acids with more than one hydrogen, in this case there's only one of the acids up there that has more than one, such as H2SO4, sulfuric acid, are called polyprotic acids. Polyprotic means many protons. What you will find in the case of H2SO4, as we'll discuss soon, is that the first proton dissociates completely. So that means sulfuric acid is a strong acid. The second hydrogen, the second proton, does not dissociate completely, and so that forms a weak acid. When the proton from HCl dissociates, it leaves behind a chloride ion, Cl- ion. A negatively charged ion can attract an H+, a hydronium ion, making it a base. Here, Cl- is a base. So what remains behind after the proton dissociated is a negatively charged chloride ion. The H+, in the absence of any other substances, attaches to the lone pair of a water molecule to become H3O+. A base that differs from its acid by exactly one proton is called a conjugate base. A conjugate acid and its conjugate base are called a conjugate acid-base pair. Think of conjugate acid-base pairs as brother and sister. They are related. And the importance of conjugate acid-base pairs will come up in a couple of weeks, and next week actually, when we start talking about buffers. A base that differs from its acid by exactly one proton is called a conjugate base. Hydrochloric acid, HCl, and the chloride ion, Cl-, are a conjugate acid-base pair. So there you see it. HCl is a conjugate acid of the chloride ion, and the chloride ion is the conjugate base of HCl. So the difference between those two is that one little blue proton right there. That's the difference, and that makes them a conjugate acid-base pair. Again, the significance of conjugate acids and bases will come later on in this unit. A conjugate acid-base pair are an acid and base that differ from each other by exactly one proton. Examples of acids and its conjugate base. So hydrochloric acid, HCl, the conjugate base is chloride ion, Cl-. Nitric acid, HNO3, the conjugate base is NO3-. Acetic acid, that's vinegar, is CH3COOH, and its conjugate base is CH3COO-. Okay, so CH3COOH, and the conjugate base is CH3COO-, and that's a conjugate acid-base pair. The importance of conjugate acid-base pairs will be seen later on. A conjugate acid-base pair is an acid and base that differ from each other by exactly one proton. Examples of bases and their conjugate acids. So ammonia we've seen before is NH3. When it adds a proton, it becomes NH4+. Bromide, which is Br-, if it adds a proton, it would become HBr. Chlorate, which is ClO4-, if it adds a proton, it becomes HClO4. The importance of conjugate acid-base pairs will be seen later on. Strong acids completely dissociate in water. This means that every strong acid molecule that enters water will give a proton to a water molecule. So what you're about to see is a very repetitious series of all the strong acids to help reinforce your memory of them. So here we have hydrochloric acid. Hydrochloric acid is a strong binary acid, HCl. All HCl molecules donate a proton to a water molecule. Here we have HI. Hydroiodic acid is a strong binary acid, HI. All HI molecules donate a proton to a water molecule. HBr. Hydrobromic acid is a strong binary acid, HBr. All HBr molecules donate a proton to a water molecule. Now we get into the oxyacids. Nitric acid is a strong oxyacid, HNO3. All HNO3 molecules donate a proton to a water molecule. Sulfuric acid is a strong oxyacid, H2SO4. All H2SO4 molecules donate a proton to a water molecule. Sulfuric acid is a strong oxyacid, H2SO4. When the first H+ dissociates, the resulting compound is hydrogen sulfate. That's HSO4-, which is a weak acid. The second proton will dissociate sometimes, but not always. That's the definition of a weak acid. The second dissociation produces the sulfate ion SO4 2-, and you'll find that on your 60 common ions sheet. So that's how some of those molecular ions are formed, is by acids dissociating. Okay, and this is perchloric acid, a strong oxyacid, HClO4. All HClO4 molecules donate a proton to a water molecule. Chloric acid is a strong oxyacid. Again, this is the one that sometimes is and sometimes isn't classified as a strong acid, but we will say that it is. That's HClO3. So all HClO3 molecules donate a proton to a water molecule. Strong bases are bases that completely dissociate in the same way as strong acids. So 100% of strong bases, when you put a strong base in water solution, it will produce a hydroxide ion, an OH-. So here are a list of the strong bases. Lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide. Now those are all in the alkali metal column, the far left column on the periodic table, and then the next column to the left, or to the right, is calcium hydroxide, strontium hydroxide, and barium hydroxide. One thing you'll notice that all strong bases have in common, they all contain a hydroxide. That's the Arrhenius definition of a base. You look at the formula and you see OH in it. So that's the Arrhenius definition of a base. You also see that they all contain either alkali or alkaline earth metals connected or attached. They're ionically bonded to those hydroxide ions. So there's the metals that are attached to the hydroxides. So strong bases contain hydroxide ions, OH. So they actually contain the hydroxide, which they then dissociate with, and the hydroxide is left in the solution. They contain an alkali or alkaline earth metals, and they dissociate 100% like strong acids. And the position of the metals in the strong bases form the letter B on the periodic table. This is just a way to remember which metals form strong bases with hydroxides. So you see that they form the shape of a letter B for base right there on the periodic table. What determines the acidity of a solution? The acidity of a solution is determined by the concentration of hydronium ions, H3O, are in solution per mole. So in other words, an acid is strong based on how much it dissociates. But that's different from the acidity of a solution, which is how many H3O plus ions there are in the water in the aqueous solution. We'll talk about that distinction more later on. It'll be made more clear. So less acidity, you see a couple of hydronium ions in the solution there. And over here, you have more acidity or more acidic, and you see more hydronium ions. Now, how did those more hydronium ions end up on the right and not on the left? Either A, you used a stronger acid, such as hydrochloric acid versus acetic acid, that's a strong versus a weak acid, or you may have used a weak acid, but used a lot more of it, poured more of it in the solution, and that would produce more H3O plus ions. So there's two ways you can make the solution more acidic, or with greater acidity. And that takes care of this first lesson. It's very important that you understand these concepts before moving on, because they're going to be fundamental in the next 3 weeks. So get this lesson done, and we'll see you on the next lesson.